The line is
Hello, hello, please can you hear me?
Yes, sir. We can hear you.
Okay, so sir, he said that his network is worrying him. He's thinking maybe it's his location, his current location, so he's trying to relocate and get back to us to go on.
Okay. Thank you, sir.
Welcome.
formula that. So as all of us know, kinetic energy, and kinetic energy normally depend on the mass and the speed. And we know that it's a scalar product because it has no direction. And we measure in joules. So if I have this 2 kilogram object moving at 4 meters per second, I know my mass to be 2 and my velocity to be 4. I'll have 16 joules per the formula. So we call something work kinetic energy theory. So this theory basically connects work and motion. Work and motion. You know, in physics, we define work as only when the force moves through a distance. There may be a force without a distance. We'll say no work is done. We may carry the whole universe. We may be sweating. So long as there hasn't been movement, no work is done. That's the definition in physics. So this theory is trying to connect work and motion. So the net work done on objects equals the change in its kinetic energy. So the net work is change in kinetic energy. So the change in kinetic energy from the initial to the final, from final to the initial. So that is a change in the kinetic energy. So that is what we say the net work done. The change in kinetic energy gives you the net work done. So when the work is greater than 0, we know that speed increase. But when the work is less than 0, the speed decrease. So when the work is equal to 0, the speed stays constant. It's basic that we know about this. When you are a work done is greater than 0, and you are trying to move, and your speed is increasing, but when you are 0, you are at a constant position. So let's look at this. That is loaded into a spring-loaded toy gun by pushing the spring in by a distance x for the next loading. The spring is compressed a distance 2x. How much faster does the second that leave the gun compared with the first? So A, 4 times as fast. B, 2 times as fast. C, the same. D, half as fast. E, the fourth, 1/4 as fast. So this is a question and we have the possible answers. How do you arrive at your answer? So the spring compressed from x to 2x, that is from the question. And then we know that energy stored in the springs is directly proportional to the extension squared. So the x is the extension. So the first case, so the energy is directly proportional to the extension squared. So in the second case, because it's 2 times, so you multiply s by 2, so you have the 4s squared. So that the energy is 4 times larger. So since the kinetic energy is equal to half mv squared, you make the v in the subject from there. What Are you getting? If you make viewing the subject. Hello?
Yes, sir.
Yes.
Hi, sir.
So looking at this equation, K equal to half mv squared. Is that equation correct? V directly proportional to square root of 4. Is that true? So you multiply both sides by 2k, and your mv. Have you gotten why the answer is supposed to be 2 times as fast?
No, sir.
Nobody's talking.
No, sir.
The dart is loaded into a spring toward that by pushing the spring in by a distance s. For the next loading, the spring is compressed a distance 2x. How much faster than the second that leave the gun compared with the first? So we have the possible answers: 4 times, 2 times, the same, half, 1/4. These are the possible answers. So we are trying to work it out together to see how we arrive at the answer. That's what we are trying to look at. So we know that the energy is directly proportional to the extension. When you pull x squared, the extension squared. So in the second case, it's double. So you use the 2 to multiply. So you have, because this one is squared, so you have 4x squared. So here, the energy is 4 times larger. So now, what is the formula for kinetic energy? Kinetic energy is half mv squared. Have your jotter, have your pen, and work this things out and see what you are going to get. So if I have this, and I want to make v in the subjects, you square root the k here. So what it means is that v is directly proportional to the square root of the k. That's what it means. So the square root of the square root of the k is what? Is what we have found here, 4. So that is 4, and the square root of 4 will give you what? 2. Are you okay?
Yes, sir.
All right. So now let's look at this question. 6.0 kilogram block initially at rest is pulled to the right along a horizontal, frictionless surface by a constant horizontal force. Find the block speed after it has moved 3 meters. So we are looking at this. So this is the block. So let's look at it. What is given in the question? The mass is 6 grams. The force is 12 Newton. The distance travel is 3 meters. So now the initial speed is 0. Why is it 0? Why the initial speed is 0?
Because the block was initially at rest.
Okay, all right. So now the first thing we will find is the work done. We know work done is force times the distance. So you find your work done first, the distance. So after finding the work done, so now the kinetic energy, half mass v squared. So half mass v squared is equal to the work done. Work done is equal to change and equal to mv squared. So you found the work done to be 36. So half the mass given is 6 and you have the v squared. So from here, you have to make your v the subject. V divided by 36 will give you 12. So v squared of 12 will give you what? 3.46 meters per second. This is your velocity. That is your velocity because that's what the question asks to find the speed. So when they ask you the speed, then you are finding the V is the speed that you are finding. So first, what we have is to be able to find, you have been given mass, force, and distance. So now the work done should be force times the distance traveled. And the work done we know to be changing kinetic energy, and kinetic energy is mass v squared. So now I know my work done, and then I have my mass, so I can find the velocity. So you're able to have this, you should arrive at 3.5, 3.46, anything close to 3, you should be right. So let's look at another question. A 5-kilogram object is pulled with a force of 20 newtons while friction opposes the motion with 8 newtons. The object moves 6 meters. Find the net work and find the speed if you start from rest. Can you put your hand to that? Can you try it?
Yes, sir.
Okay, try it. Let's see. You have only 2 minutes. Today, because we are behind, we need to move a bit faster. All right, let's do it together. So what is given? The force, the applied force and the frictional force, and the distance travel, and the mass. So the net force should be the pull. You are applying the force, pulling the object, and there is a friction. So you need to subtract the frictional force from the pull force. That will give you your net force. So that will give you the 12 Newton. So the work done is the force, which is the 12, and the distance traveled is 6. So the net work done will be 32 joules. So now you go back to the kinetic energy formula. Work done equal to the kinetic energy. So we have found the work done. So it's given in the questions the mass, which is 5. So yours is to find the speed. So that's the velocities. So as you compute these values, you should get something close to 5.37. Yes, if you do something, you should get something close to 5.37. 37. You take your time and go through it and see whether you arrive at the same value. The ball speed up from 2 meters per second to 10 meters per second. Its mass is 1 kilogram. Find the change in kinetic energy. Yes, 1 minute. All right, let's do it together. So the change in kinetic energy is so initial minus the final. So we have the initial and the final, and we have the mass, so half times, and then she's able to arrive around 48 joules. Change in kinetic energy, so that means you are moving from initial to final. She's able to do that, and there's a mass given to you, and then she's able to get it done. The V, the velocity that it's moving, we have the initial and the final. So that's what you're supposed to get. Is there something need to be clarified? Is there anything that you don't understand? A spring launched 0.5 kilogram objects. The spring store 200 joules of the energy. Find the speed of the object as it leaves the spring. So all the spring energies, the kinetic energy. So 200, the kinetic energy is given. So you should be able to get. So we are just using the kinetic energy formula. As you want to find the speed, find your velocity. This is just mass. You put in your values, and then you are cool to go. So we have some few examples that you can try on and see how you understand the concept. So if you talk about kinetic energy, you definitely have to talk about potential energy. So potential energy is the energy possessed by a body, its position. So a body that is at a particular position possess potential energy. And that potential energy could be given a force, could be changed to kinetic energy. So before the kinetic energy, the object possess what you call the potential energy. So before kinetic energy, the object possess potential energy. So kinetic energy is all about where the object is. Where is the object? So that's potential energy. So when the object starts moving, you change from potential energy to kinetic energy. We call something gravitational potential energy. So you are talking about the vertical movement because the Earth pull every object towards the Earth, which we call the gravitational energy. So once we talk about gravitational potential energy, we are talking about vertical movements. So you'll be talking about the mass as a shift due to gravity and the height. These are the concerns that you look at. So we know that potential energy or the gravitational potential energy is given as the mass as a shift due to gravity and the height. So we know gravity to be fixed at 9.81 meters per second squared. So that is a value that we know for gravity. So at any reference point, that will become your height that you use. So basically, potential energy depends on the heights. The heights, that is the only thing that it depends on. The roots doesn't matter, but it's the heights that we are so much concerned with because it's a vertical movement. It's not horizontal movement. And it's a scalar quantity. And the unit is joules. So when you lift an object, you do work on the system. That energy is stored as a potential energy. When you release it, the potential energy is changed to kinetic energy. Let's take this as an example. You have a book on your table right now. It's possessing potential energy. So just push it, drop. The potential energy is converted to kinetic energy. So where is the object? The position of the object is what we are referring to as the potential energy. As the object starts movement, the potential energy is changed to kinetic energy. So let's take this as an example. When you are lifting slowly, when you are lifting an object slowly, you realize there's no acceleration. So the work done should be equal to the potential gravitational force. So the work done should be equal to gravitational force. So work done on the system should be equal to the change in potential energy. So change in potential energy is equal to the work done in the system. Change in the potential energy. So when there's a change, potential energy starts moving into kinetic energy. So we talk about that work done on the system equal to the change in the potential energy. A work will only be done when you're able to disturb the system and there will be a movement and the potential energy is off. So now let's look at this. 2 kilogram object is lifted to a height of 5 meters. Find its gravitational potential energy. So you know your formula to be mass acceleration due to gravity and height. So just compute it and then you get your answer. You compute it, you get your answer. So when body gets to the top, at the temporal moment, there's no movement. The kinetic energy will be 0. So now the potential energy is possessed, that potential energy at that maximum height. But when it's moving from the height down, the potential energy will be 0 and the kinetic energy will be in maximum because it's dropping, it's coming down. So kinetic energy. So mostly we talk about at the top or at the height there, the kinetic energy will be 0. And at the bottom, the potential energy, at the bottom, the potential energy will be 0. The movement, that's what we are talking about. So we try that they balance the potential energy and the kinetic energy balance at that point. So that's what we normally refer to as energy conservation. There's a kinetic energy, potential energy. At each point, you see there's a potential energy or kinetic energy. When you hold the kinetic energy constant, the potential energy vary. But when you hold the potential energy constant, kinetic energy varies. So that is what is happening. They work hand in hand. Kinetic energy, potential energy. You change the kinetic energy, you get the potential energy. Either you are running or you stop. So what it means is that potential energy is the energy due to position. And work done is a change in potential energy. So we know that potential energy mostly depend on the heights and then have a reference point. So if you talk about periodic motions, we want to talk about motions. Periodic motion is a motion that repeats itself after equal time interval. As we know about sinusoidal waves, periodic motion is a motion that repeats itself after an equal intervals. When we talk about the pendulum, swinging pendulum, the experiment that we have done in SHS, you hold the bulb, you tilt it, it goes to and fro. And we have vibrating springs. You tie the spring, it vibrates to the end. And the earth orbiting around the sun, the earth orbiting around the sun. So at every point, there is a time. So sound waves, sound wave, sound wave, sound wave. So now, oscillatory motions. Oscillatory motion is a type of periodic motion where the object moves back and forth about equilibrium position. So basically, what would be example? Object move back and forth, its equilibrium position. What would be example of oscillatory motion? Oscillatory motion. Example?
A simple pendulum.
Simple pendulum. That's true. So we call a harmonic motion is also a type of oscillation motion. So the condition for simple harmonic motion is that the force is proportional to the displacement. The force is proportional to the displacement. So that's why if you are conducting the simple pendulum experiments, you are expected to tilt the ball through a small angle, less than 10 degrees. So from there, you're able to get the exact experiment value, 9.8 should be approximately to 10. But when the angle is when the angle is large, you are likely not to get the 9.8 value for the acceleration. So this experiment helps us to appreciate the work done. Mostly when you are a scientist, you have discovered something, it's good to put the procedure down that anywhere on the earth that you are, you should go through the same procedure and get the same results. That's why go to your lab, simple pendulum experiment. You could calculate the gene to be equal to 9.8 or 9 point something, 9 or 10. Approximately should be 10. So you should be able to get that value in your lab because the procedures has been done and you need to follow through and the condition that will make you not to get the same result is what we call your precautions. It's things that you're supposed to do. But if you don't do them, you are likely not to get the same results. If you don't do them, you are likely not to get the same results. So the sources of error, you should know them very well and know exactly what you are doing. Yes, when we talk about waves, there are some things that we need to know about the waves. When we say amplitude of the wave, what does it mean? When we say amplitude of the wave, what does it mean?
So the maximum value.
That's the maximum value. When we say period of the waves, what does it mean?
So the time taken by a wave to complete a cycle.
So when we say the frequency of the waves, what does it mean?
The frequency is the occurrence. The number of occurrence Uh,
All right. So when we see this diagram, we can see the A here and the T here. This is the amplitude and this is the period. So see the amplitude from the A here, you see the amplitude high and you see the amplitude low. So we have the highest, lowest. So we have this at every point, we have the amplitude, but you check the period, how called it, each of the highest points. This one give you the period. So when you are given a diagram to find the period or the amplitude from the diagram, you should know you're able to trace this value to your S value and trace this one to the next X value and you subtract it. That will give you your period when you are using graph to determine your period. And you pick your amplitude from the y-axis, what you have, that's what you pick your amplitude from. If it is a diagram, that you are picking the amplitude from. So now we are talking about how the period, so long as you know the period, you could find the frequency. How does the period relate to the frequency? The period, how does it relate to frequency?
okay, so the period deal with the time, and the frequency is
So what's the relationship between the frequency and the period?
okay. So sir, the frequency is how fast the wave. So the relationship to be, the frequency is how fast, and then the period is let me come back.
Sure, good attempts. Yes, who else?
Hello, sir.
Yes.
Please, says so the frequency is inversely to the period. It's inversely
Yes.
related to the period.
Yes. As the frequency increase, the period decrease.
Yes, sir.
As the frequency increase, the period decrease. So they are inversely proportional. So anytime that you're able to find the period using your graph, you can use the formula to find the frequency. Can use the formula to find the frequency. You can use the formula to find the frequency anytime that you have. That's no. And we have angular frequency. You have angular frequency. So basically, we are talking about angular frequency. We are just trying to look at that moves in, if a direction is moving in a certain direction. So this is moving direction. So we refer to them as, so see, if you have this one, the amplitude of the motion is simply the maximum value of the position of the particle in either the positive or negative X. So you have, or amplitude could be positive, it could be negative. So the constant angular frequency, it has a unit of 1 radian. It's measure of how rapidly the oscillations are occurring. The more oscillations per unit time, the higher the value of angular frequency. So we have the angular frequency to the K is the number movement at the M. So mostly we talk about the K mass. So these are the relationships that you have to know. This is the angular, the omega is equal to the square root of the K and the mass. So we have the period to be 2 pi over omega. How do we arrive at this? How do you arrive at 2 pi over the omega?
Hello, sir.
Yes.
I think we have another formula which is 2 pi f, and then the 2 pi f with the f is the inverse related to the with the time.
Great. The omega is 2 pi f. So if the omega is 2 pi f, so take your f, and then the f is equal to 1 over t. So if f is over 1 over t, and then what is your t? So what is your t? So you're able to have to replace the 1 over t. So this will go up, and this one will come down. You have this omega is equal to 2 pi f. And then this f will be replaced. So you have 2 pi t. Because f is 1 over t. So this one is at the top. So you multiply 2 pi, multiply by the 1, the inverse. So it's over t. So the omega will give you 2 pi t. This is your omega value. This is your omega value. So when you have your f to be 1 over this, and then your w will be over this. So if you are taking the inverse of this, you get a 2 pi. So basically, when you understand the omega should be 2 pi f, and you know your f to be 1 over t, you should be able to manipulate any of this value given to you. You should be able to manipulate any of this value given to you. That's how it's supposed to be. Let's say, for example, here, we have the 2 pi over t. So now, when you get to this level, 2 pi over the omega, 2 pi over the omega, this is the t values. The t value is 2 pi over the omega. So now you are trying to replace it. And then don't forget this value, the omega, the square root of k over m. The omega is square root of k over m. So now, this is the omega that you are replacing, square root of by k, because it's 1 over. So you're able to take this one, the inverse of this value. So you're able to take the inverse of it, so you're able to arrive at this value. So now your f is 1 over t. So what we are going to look at is that this is the 1 and this is the omega. So your omega value here, so you're able to have this in this dimension. So basically, the initial equations, if you know omega, which is 2 pi f, and you know your f to be 1 over t, you should be able to manipulate the equation given to you. You are just replacing each of them anywhere that you found them. You're able to replace them, and then you are cool to go. That is what is happening. Now, let's look at velocity. When you differentiate velocity, we get acceleration. when you differentiate velocity, we get acceleration. This is a elective mass that all of us do, that when you differentiate velocity, you get acceleration. But when you integrate acceleration, you get velocity. Differentiation and integration, they move hand in hand. When you are moving forward or you are coming back, minus 1 plus 1. That's the rule for differentiation and integration. So if you have this value, you have our waves, angular velocity, and lambda, the amplitude. This is an equation that we normally use for waves. So when you have these waves, when you differentiate this value, when you differentiate sine, you get cos. When you differentiate sine, you get cos. So this is the omega here. You differentiate it, count omega square, acceleration, this become cos, and this remain the same. But this is what we are differentiating. So differentiate velocity, you have d squared x dt squared. You are going to have next, of course, theta of this. So now we are talking about the maximum velocity. At the maximum velocity, the omega is multiplied by the amplitude. So basically, the omega here from our previous formula is k over m. So I'm just replacing this with the omega here. They are replacing it. And the maximum is v squared. So instead of the v squared, I'm writing the v, that's why the square root. So you have your a here. So you have your a here. This is your a here that you have. The omega, you see that here the omega is squared, but when you take off it, the omega become 1. The omega become 1 here. So omega and the amplitude. So you're able to have this as, so this one is for the omega and the amplitude is here. So you're able to have the V maximum. You have your wave number mass multiplied by the amplitude. But when you come to acceleration, you have the omega squared, the amplitude equal to the over A. You see that these have been removed. Because when you square this value, it's removed the square roots, but this value is squared. So this is what we have in this regard. So you're able to have this as acceleration maximum. So this is a formula that when you are asked to find the acceleration maximum or the velocity at maximum, use, if you have the omega amplitude, you're able to use. Or if you are given the wave number, then you are going to use this instead of this. So depending on the value given to you, let's check from this diagram. You see the maximum from the reference point, the S line, to the maximum. This is what we call the amplitude, the maximum displacement. These are amplitudes, and our period is shown clearly from this dimension. So you're able to get this. So you have your maximum acceleration from and the maximum velocity depending on the graph. If the velocity time graph, you are finding the maximum velocity. If it's the acceleration time graph, you are finding the acceleration. So depending on the graph that you are plotting, that's what you are going to find the velocity maximum or the acceleration maximum. So depending on which one that you are finding, that's what you get to. So now we know about Hooke's law. What is Hooke's law? What is he saying? Do you remember Hooke's law? Hello? Hello?
Yes, sir.
Am I here? Okay, I thought that my network is gone again. Do you remember Hooke's law? What is it saying? Provided the elastic limit is not exceeded, the force applied should be directly proportional to the extension. So we have the force, extension is the S, the extension is the X, and we have the force applied directly proportional to S. So because I'm bringing the equal to sign, I need to bring the spring constant value. And as you stretch, and we have this movement, that's why you have the negative value here. So the force applied is directly proportional to the extension. So the negative sign is the force is restoring. You pull it, you have to come back. So the negative is the restoring force. That's why we put the negative sign attached to the Hooke's formula. Is the restoring force, because spring, when you pull the spring, it goes in and come. So the restoring force is what we use the negative sign to indicate that there is a restoring force. Basically, that's what we want to look at. So looking at this diagram, the A, B, and C, you see a pull block to A. Here you have A. The S is equal to A. And then you release it and move towards the center at the speed. So the center, at the center, the speed is at maximum. At the center, the speed is at maximum. So you move to X, which is on the negative side. It's slowed down. So when you stop, it's reverse. When you stop, it will reverse. This repeats continuously when you're using the springs. You're using the springs. So this continual action move to the center. The speed is at maximum. And we have both the negative and the positive side. And this is something that repeats itself. So now what we know about the Hooke's law is that we see the force is equal to the spring constant minus screw constant and extension. And then what do you know about the force? The force is mass times acceleration. The force is mass times acceleration. So now, when I replace my force with mass times acceleration, and I want to find acceleration, I'll divide this by the mass. So this is just the mass times acceleration. So if I want the Boolean acceleration, and I'll divide this by the mass. So you have your K over the N multiplied by the extension. The minus sign still remain. So that's what we have here. Acceleration always points towards equilibrium. So the bigger displacement, the stronger the pull. So this is what is happening. So when you displace the ball, Hooke's law, if you're able to displace, you pull it. You need to pull to get a bigger displacement. That's what it means. So basically, this is the Hooke's law, replacing the force with mass times acceleration. And then you are putting at the acceleration. So you divide this one by the mass. So able to get the acceleration. So let's look at this. A block on the end of the spring is pulled to a position X times 5 and released from the rest. In one full cycle of its motion, through what total distance does it travel? A block on the end of the spring is pulled to the position X 5A and released from rest. In one full cycle of its motion, through what total distance does it travel? The A over 2, B, A, C, 2A, D, 4A. How do we arrive at the answer? The bulk moved from X to A and complete one full cycle. So you move from A, 0, minus A, 0, A to A. So the total of the A will be 4. From A to 0, from 0 to minus, from minus to 0, from 0 to A. So this will be the movement. So it's 4 of the A's. So 200-gram block connected to a light spring for which the force constant is 5 Newton per meter is free to oscillate on a horizontal frictionless surface. The block is displaced 5 centimeters from equilibrium and released from rest as in the figure below. Find the period of its motion, determine the maximum speed of the block. What is the maximum acceleration of the block? So we have this, the initial velocity is 0, the amplitude, and the time is 0. So now that we can see the amplitude, go to the initial here. So find the angular frequency of the block. You know the angular frequency is equal to the number wave by the mass. So the number of the waves given is 5 Newton. So angular frequency finding should be very easy to do. So after I have gotten the angular frequency, and they want you to find the period. So what is the period? 2 pi f, so over this. So you have your period to 2 pi over the omega. So the omega is what we found, and these pi values that we know, if you compute it, you should have something closer to 1.26. From the formula that we know, you're able to compute this. So they want to determine the maximum speed of the block. So as we know the maximum speed to be omega and the amplitude. So the omega value is this, and the amplitude value that we have, you multiply, you have 0.25 meters per second. So basically, and then they want to calculate the maximum acceleration. So this is the formula for maximum acceleration, omega squared amplitude. So the values of the omega that you have, you square it in the amplitude value, and then you're able to have the 1.25 for the maximum acceleration. Wave motion. We know about wave. Wave transfer energy, but not matter. The waves transfer energy, but not matter. I don't know if you really grow up in the village where maybe sometimes when you go to the poolside and you drop a stone in the pool or you draw a stone in the water, you see the waves. It moves outwards. But the water still remains. The water is at its position. The water doesn't move, but the waves is what is moving. You drop the stone in the water, you see that the waves will move, but the water itself is standing. The water is standing. That's the wave. If you sometimes go to sports stadium, when we are sharing our favorite team, you see when they score, we cut up and raise the hand. Hey, we move our hand in this way. That's a wave. But your body still stands. We transfer the energy. See the energy that you are using to move. But you are not transferring the matter. Body, you are not transferring it. That is what is happening. So that's what we are talking about, waves. That's what we are talking about, waves. That's what we are talking about, waves. So now these waves, we have two forms of this wave that we talk about, mechanical waves and electromagnetic waves. And basically we say that mechanical waves need medium to be transmitted, and the electromagnetic waves need nothing like a medium. You can easily get to the other end. If you talk about mechanical waves, it can't travel through a vacuum. Mechanical wave cannot travel through a vacuum. So it's just like a sound. There must be a medium where it travels. There must be a medium, a sound. There must be a medium that it travels. So basically, you agree with me that something may be happening on the moon and you are not hearing it from here because there hasn't been a medium for it to travel. Yes, if there's a medium for it to travel, we have heard it because it's a mechanical waves. So it required a medium for you to hear. So if I ask you to explain what is happening on the moon, you on the earth, you cannot hear it. Basically, it's about the sound. It has a medium. You need a medium to be transmitted. So when there's no medium, there's no way that you hear that. But when we come to electromagnetic waves, required no medium. There is no need for a medium. It's just like a visible light. It travels in a vacuum. Having radio, you are here. Radio at Tamale, you can hear what is happening. Yes. Can you get this thing from Tamale to this side? No. But you could hear it. It travels. It doesn't need medium to be transmitted. So X-ray, microwaves, all this need no medium for them to be transmitted. That's why you're able to make call, you're able to get other things working for you. That's the requirement. So this, the types of waves that we have: mechanical waves, electromagnetic waves. These are the medium. Mechanical waves require the medium. So we talk about sound waves. There must be a medium where you can transmit that. That is what is happening. So as I'm talking, you are hearing, is it mechanical or electromagnetic? Hello, are you following? Are you here? I hope I'm not talking to myself.
No,
Yes,
sir.
sir.
No, sir.
Have you heard my question?
Yes, sir.
So as you can hear, what type of waves are you hearing? You didn't get the explanation, right?
Sir,
You
please,
didn't get it.
it's mechanical waves
Why do you say it's mechanical waves?
because it requires a medium, which is the speaker, before we can hear.
The medium is the speaker. You see where you are located and then where I am. Can you connect the speaker? Can you be playing a music at your end with your speaker? Boom, 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 boom. And I'm here and I can hear it. Is it possible?
No,
No, sir. No, sir.
Yes. What you are doing is a sound that you are producing, and a sound need a medium to be transmitted. So basically what you're trying to talk about, mechanical wave, electromagnetic waves, is that which one requires a medium? Do you need a medium to transmit it? If it requires a medium, yes, it's classified as mechanical. But if it doesn't need a medium, it moves in a vacuum, it's electromagnetic. That's why radio broadcasting from the north, you can listen to it here. Right now, my location, far away from you, but you can hear my voice. You can hear my voice. It's electromagnetic. Doesn't need a medium. Yes, that's what it means. You must get this one clear. How you able to differentiate between magnetic and electromagnetic waves, mechanical and electromagnetic waves. So what to differentiate them? If you require the medium, or you don't. Radio is what we are doing right now, just like you are broadcasting. I'm somewhere talking and you are somewhere listening. What? Using the satellites, using the other, we're able to get what's being get from the other side. That is what we call electromagnetic waves. But as I gave you an example, when the thing has to do with sound and what is happening on the moon, you may not hear it because they require the medium. You'll be at your place and be playing music at the funeral ground. I'm here, I don't know what is happening there. Why? Because they need a medium to transport it. Transmission requires a medium. So it's not possible. So propagation of disturbance, so waves movement, we have these two types, the distance of the particles. So we talk about the transverse or longitudinal. When you say something is transverse, so the particle is moving perpendicular to the wave direction. So you are using the rope, that you are tackling a rope. So you're wangling a rope. You realize that the particle moves perpendicular to the wave direction. So for it to move like this in front of you, holding the ropes, you are trying to juggle the ropes. See that the movement, the particle moves perpendicular to the wave direction, where the wave is going, move wave direction. But if you talk about longitudinal, so the particle move parallel to the wave direction. So when you are using a spring, so you see what is happening, you move parallel to the wave direction. You compress, release, and release. So it moves parallel to the wave direction. So sound wave, seismic waves, the primary wave, the P waves, all these things are longitudinal waves. But when we talk about transverse wave, we are talking about light water surface waves. So when you drop a marble in the water, the surface waves. So these are transverse waves. That's what we call them, transverse. But if you are talking about the seismic wave, you see how the earthquake happened. Have you experienced earthquake before? Have you been there earthquake occurred before? Have you experienced earthquake?
No, sir.
Oh, nobody here have experienced. You don't live at McCarthy Hills, eh? You don't live at McCarthy Hills. You don't live at McCarthy Hills. So what we call pulse and waves. The pulse basically means the single disturbance, but the waves, the continuous disturbance. So that's a wave. So we move in that dimension. So there are some waves that exhibits transverse and longitudinal, just like the sea water. Have you been to the beach before? Have you swum in the sea before? Have you been to the beach?
Yes, sir.
Yes. See how the waves, when they are coming to the shore, so how they behave. So they possess both the longitudinal and the transverse waves. The motion of a water element on the surface of a deep water in which a wave is propagating is a combination of transverse and longitudinal displacement. The result is that the element at the surface move in nearly circular path. So sometimes that water from the sea can carry you away, can pull you together and send you away because of the stress. So you see this one, we have the crest at the maximum, the trough at the minimum. So the waves is moving up and down, and it has a lot of velocity, possess that velocity. So our time is almost up, especially the wave equation that we use. This is the common equation that we use for traveling waves. So we have the wave number, the the omega, and the phase shifts. So we have the amplitude, the wave number, which is the 2 pi over lambda, and the omega is 2 pi f. We have the frequency, we have the velocity, which is the frequency times the lambda, and the phi is the phase shifts. So finding the characteristics of the sinusoidal wave, you find the amplitude, wavelength, the period, and the frequency of the sinusoidal wave. You write out the wave function in the form. So the wave functions were written in this form. So the amplitude can be read straight from the equation and it's equal to A. So from here, the amplitude is A from here. So the period of the waves can be derived from the angular velocity. So if they want you to find the period, so you have your 2 pi over the so if you're able to have this, you can find your period from this. So the frequency, when you know your period, you could find the frequency from the period. So the wave can be found using the wave number. So the lambda is 2 pi over k, because you can just get it from the other equations to be able to have the 2 pi over k. So this is what you have that you can easily use to get the equation. So let's look at this question. A transverse wave model with a wave function. So these are the functions of the waves. So this is the general equation. So we have 0.2 meters sine 2.2 meters. The x is here, and 1.5 meters t. So now find the amplitude, the wavelength, the period, and the speed of the waves. So straightforward, the amplitude will be this. When you compare these two equations, you compare the two equations. So straightforward, you get your amplitude to be this. So your wavelength, you could find your wavelength. So the amplitude from the questions will be A. And the wave number, when you compare the equation, will be 6.28. And the omega from here should be 1.57. So you could get this one from the question direct by comparing to the original equation. You're able to take this one out. But now they want you to find the wave number. So for you to find the wave number, you should be able to use the formula to get a wave number. The wave number. So we have this, because you know the k from the equation. You just take this over the k, you're able to get the wave number. And the period, you want you to find the period, which we know you can find the omega with 2 pi over the period. So your period, you'll be able to find this over the omega, and you have it. So if you know your period, you can find your frequency. If they ask you to find the frequency, that this one is 1 over, you could be able to find that. So they say want you to find the period, the speed of the wave. So we know the omega over k, the speed of the wave. So this wave equation, we compare with the equations, we're able to pick the values from those one that you need to calculate. You're able to use the equation to get it done. Basically, this is what we can do for today. Let's some time and go through the rest that I have. They are reading something that we can go through, be able to get it done. Today we struggled to get the class, but I believe that the network will help us next time to be able to do it in a very better way. We have to rush to get things done. Sorry for the inconvenience though. Thank you for your attention for today.
Thank you, sir.
Who are the people here?
Yeah,
Please,
yeah. She said, yeah, yeah.
Is that?
Yeah, yeah.
Oh yeah. Except the lady. Except the lady. Everybody's here except the lady, eh?
yes, sir.
Alex,
Yeah.
Bernard. Oh, okay. Joas, Sadat, Zakari, Sidhu, Samuel. Oh, okay. All right, that's fine. Thank you for coming. You have your slide. We'll have time to have a better interaction on this. Thank you. Enjoy your day.
Welcome, sir.
Thank you,
Yeah.
sir. Have a nice day.
Okay.